Hello and welcome back to another lecture from Organic Chemistry. And as usual, thank you very much for watching this lecture video. Our subject for today will be pericyclic reactions, reactions of conjugated pi systems. And there are that kind of reaction that usually they will go forward without creating a partial positive or negative charges. And also we're not going to have intermediate. That means like entire the reaction is going to happen in one cycle. So no positive or negative charge. Inside the meaning of this, you can say solvent, and the solvent will have no effect on rate of reaction. So I'm going to say that the solvent will have no effect on the rate of reaction. Rate of reaction. Okay, we can classify them to three sections, and one is going to be the cycloaddition, next one will be electrocyclic, and the third one will be sigmatropic rearrangement. And the difference between them, the first one, you take two pi bonds and you turn them to two sigma bonds. So the change with pi is going to be equal to -2, while the change with sigma will be +2. And remember that sigma bond is stronger than pi bond. So that's a good thing that we are technically the reaction is doing. It takes pi and turn it to sigma, and it's making technically the bonds are stronger and stronger. And next one, it will take only one pi bond and it will turn it to one sigma bond. So the change with pi bonds, it will be -1, while the change with sigma, it will be +1. And the third one, the sigmatropic rearrangement, there will be no change with number of pi or sigma bonds. So that means change with pi, it will be equal to 0. Okay, we had two pi bonds and we got two pi bonds. How about sigma? And the change with sigma, I'm going to say this one also it will be 0. The only thing that happened that we moved position of the double bonds, and as you see here, this one on the left side we used to have a sigma. Now the ring, like technically the ring, it kind of like flip, and the sigma bond went to the right side. Okay, let's review the common characters of pericyclic reactions. One, the reaction is cis-concentrated. What does it mean? That means the reaction is going to happen in one step. Okay, so in one step. If it happened in one step, that means that there is only one activation energy. Okay, we are not going to have two or three of them. Also, there will be no intermediate. So one activation energy and no intermediate. Okay, and the reaction says reaction is involves a ring of electrons. And what does it mean? Imagine you have such a system, and this one it wants to react with ethyl. There will be interaction between those two parts, and that's going to give you a ring. And electrons can actually circle inside that ring clockwise or counterclockwise. In both directions, it can happen. Transition state is cyclic, and as you see, I showed actually the transition state or the interaction, and like in the ring. And the last one says the polarity of solvent will not have effect on rate of reaction, again because we are not creating a positive or a negative charge. And there is no positive or negative charge, that means you're not going to have dipole hydrogen bonding or ion dipole interaction, and maybe like the dispersion forces, but the dispersion force is really weak, and because we're not creating much positive and negative charges, so I'm going to say it is not going to have effect on rate of the reaction. And how much dispersion force is really involved, okay? And I can't say much about that one, but I can say for generally I can say that it's not going to have effect on rate of the reaction. I already reviewed this, and as you see, like from cycloaddition to sigmatropics, the change with pi bonds, number of pi bonds is going down. And when we reach sigmatropic, there will be no, technically, there will be no new, we're not breaking any pi bonds. And it's just simply we can change position of the sigma bonds. And that's the reason we call it sigmatropic rearrangement. let's go through some example. And the first one that we're going to review it will be the Diels-Alder reaction. So we're talking about cycloaddition reaction. And the first one, and it's a cycloaddition reaction, and I'm going to practice some example about it. So we're going to say this one is cycloaddition reaction. Okay, cyclo, that means we are going to build like a cyclic compound, and we are adding some stuff to each other. And I'm adding, in this case, I'm adding four p orbitals to 2p orbitals from another molecule, or I can say I have 2 pi bonds. Okay, 2 pi bonds, and I'm adding them to 1 pi bond. Totally, I have 6 p orbitals involved. And the way we represent it, or we show it, we open a bracket and we say 4 plus 2. That means one of the reactant, it has 2 double bonds, and in the second reactant, it has only 1 double bond. Okay, reaction is going to happen in one step again. So there is only one step, and we will have only one activation energy, and there will be no intermediate. And Diels-Alder reaction, it will be like technically favored if the temperature is low. And the common temperature that we use for Diels-Alder reaction is 0 to 200 degrees Celsius. Now, what will happen if we raise the temperature? If we raise the temperature, the reverse reaction or the retro reaction is going to happen. So the forward reaction, this is the forward reaction. You have diene reacting with alkene, and it will go through this barrier. That's going to be the activation energy, and it will give you a cyclic compound, and that's the reason we call it cycloaddition. We started with 4 pi, 4 p orbital. We added them to 2 p orbitals, and we got one cyclic molecule. So I'm going to call it cycloaddition. Next thing is again, there is no intermediate, as you see. Now, if I raise the temperature, the reverse reaction is going to happen. A cyclic molecule will break to 2 components, and technically to the starting components. And that's going to be the dominant reaction. So highlight this part. Say the Diels-Alder is going to happen when the temperature is something between 0 to 200 degrees Celsius. But if the temperature is higher than 200 degrees Celsius, then the return reaction is going to be dominant. Okay. What's the reason for it? Why we get different products? It depends, like what temperature we are actually using. When I say different product, I'm talking about like whether the reaction is going to move forward or go back. Okay, let's review this. Okay, example we can use is this example. So let's draw a molecule, diene molecule. Okay, next I'm going to add it to one alkene molecule, whatever, and then like substituent attached to it. It doesn't matter. Okay, next thing that we're going to say. Right now we have 4 p orbital here, 2 p orbital. Okay, I'm adding 2 molecules to each other, and that's going to give me a cyclic molecule with 1 double bond. So I added those, and I got 1. Okay. And what we did, we started with 1, 2, 3 pi bonds, and we ended with just 1 pi bonds. So 2 pi bonds turn to 2 sigma bonds. We know energy, the bond dissociation. Okay, the bond dissociation energy. What does it mean? It means the energy that you need to apply to break the bond. The bond dissociation energy for sigma bond is bigger than pi bond. So delta H for this process, for taking pi, turning it to sigma, delta H is going to be negative. Okay. Next, delta G is equal to delta H minus T delta S. If delta G is negative, in that case, we say the reaction, it will be spontaneous. The reaction will be spontaneous. Yes. What does it mean? It can happen by itself. Okay. It will be favored. Now, I know this one is negative. Okay. But let's check the entropy. What's the entropy? Entropy, how much, technically, how much randomness you have with the system. Or how about this? How many molecules you started with? How many did you get at the end? I started with 1 plus 1. I started with 2 molecules. And I ended with 1 molecule. So I combine them. And because I combine them, the entropy is going to go down. So I'm going to say the change with delta S of the reaction is going to be a negative number. Okay, let's put a negative number here. Okay, now negative to negative is going to make it a positive. Okay, what will happen if minus T delta S, okay, is bigger than delta H, which is negative? In that case, delta G, it will be positive, and it will be non-spontaneous. Okay, so I'm going to say this one, it will be non-spontaneous. spontaneous. That means it cannot happen. Okay. Now, how can I push it and say reverse it? If T goes up, T multiply delta S, whatever the delta S. If T is really high temperature, then this number, when you multiply to delta S, it will give you a big positive number. And when you subtract delta H from it, delta G at the end, it will be positive. And that means the reaction, it will be non-spontaneous. So say this: if T is low, in that case, delta H, which is negative, it will be bigger than minus T delta S, minus T delta S. And that's going to give you, this one is going to give you negative delta G. So it will be spontaneous. But if T goes up, in that case, you go minus T delta S, which is going to be this one, overall is going to be positive. It will be bigger than delta H, which is a negative number. And that's going to give you delta G bigger than 0. So it will be non-spontaneous. Well, the first one was spontaneous. So this is the reasoning behind it. Why do we need to keep the temperature low? If we keep the temperature low, in that case, delta H, it will be the dominant factor. But if you increase the temperature, then entropy, which is randomness, is measuring the randomness of the system, how messy the system is, then that one is going to be dominant. And so as temperature goes up, the reverse reaction will be dominant.